And for this problem, we have that Moore's law says that the number of transistors in a dense integrated circuit increases by 41% every year. In 1974, a dense integrated circuit was produced with 5,000 transistors, which expression gives the number of transistors in a dense integrated circuit in 1979. So this one's a little bit trickier since we're not explicitly told our growth rate as a number. We're given a percent. And if something increases by 41%, that means it's going to take the original amount. Let me use a different color. So it's going to take the original 100% and then add 41% to that. So this is we can call it the growth rate. And let's turn this into a decimal. So 100%, remember percent just means divide by 100, so that's 100 divided by 100. And we're going to add this increase, which is 41 divided by 100. Adding fractions, we just add the numerators since our denominators are the same. And let's rewrite this as a decimal since 141 hundredths is really just 1.41 since 1 is in the hundredths place and we have 141 of them. So our growth rate is 1.41. Or effectively, every year, we're going to multiply the amount that we currently have by 1.41. And we start with 5,000 transistors. So to start this problem in 1974, we have 5,000. In 1975, we're going to take that original 5,000 and increase it by 41%. Or in other words, we're going to multiply it by 1.41. And in 1976, we will take the previous amount that we had from the year before, that 5,000 times 1.41, and then multiply that by our growth rate, by that 1.41. Or in other words, after 2 years, we have the initial amount multiplied by that growth rate squared. And you can see this pattern continues. Let's just look at one more year here, and then we can generalize. So 1977, you take the previous year's amount, that 5,000, multiplied by 1.41 twice, and we're going to multiply this again by our growth rate since it's again increasing by 41%. So we multiply again by 1.41, and we can rewrite this as 5,000 times 1.41 to the third. So like we looked at in the previous problem, the general expression is that you take your initial amount, you multiply it by that growth rate, whatever the amount of time required is. And by 1977, we're looking at 3 years later. This is year 1, year 2, year 3 after we started. So if we wanted to, we could generalize this and say that after, let's say, t years, the number of transistors we would have would be 5,000 multiplied by 1.41 to the t power. And we're looking at the expression that gives the number of transistors in 1979. So 1979 is 5 years later. So in this case, t would be 5. So our result, 1979, would be this 5,000 multiplied by 1.41 to the 5th power. So we just need to match this up with one of the answers. And you can see that choice letter A would be correct. Now it doesn't look exactly like we have it because here we split up the 1 and the 0.41. But we know that 1.41 is equal to 1 plus 0.41. So this is equivalent to what we have here. And often you do see it written like this, where you have this 1 plus whatever the amount you're increasing it by. Since notice that's essentially how we found the growth rate to begin with. You had this 100%, and then we added what we were increasing by. And you could even generalize it if you were decreasing it by a certain amount, you would just subtract. So we have this 1 plus 0.41 for our growth rate here. So let's move on. Let's look at one more of these problems. And in this one, we have a manufacturing plant earned $80 per man hour of labor when it opened. Each year, the plant earns an additional 6% per man hour, which expression gives the amount the plant earned per a man hour of labor 3 years after it opened. So we start with $80 per a man hour of labor, and we're going to increase it by 6% every year. So this is just like our previous problems, where let's say we have time, and we can use E for earning. So at time 0, it's earning $80. And our growth rate, we have this 6%, and we're going to add that to the original amount since we're increasing it by 6%. So really, we're taking 100% of what we have and then adding 6% to that. So let's just turn these to decimals. 100% is really just 1. 6% or 6 hundredths is 0.06. So our growth rate is just this 1.06. So every year we're multiplying the earning amount by 1.06. So in year 1, we'll take this $80 and multiply it by 1.06. In year 2, we take the amount we previously had, that 80 multiplied by 1.06, and we're going to multiply by 1.06 again. And then in year 3, we'll do the same thing. We'll take the previous amount, the 80 multiplied by 1.06 times 1.06 again, which we could just write as 1.06 squared, and multiply that by 1.06 to account for the fact that it's growing every year by that 6%. So in the third year, which is where we want to stop, our expression is just 80 multiplied by 1.06 3 times. So we can write that as 1.06 to the third power. And remember, this 1.06, we could write it as 1 plus 0.06. So this is equivalent to 80 multiplied by 1 plus 0.06 to the third power. And if we want, we could write this out 3 times. And looking at the answer choices, that does seem to be what they did here. They took 80 and they multiplied it by this 1 plus 0.06 3 different times. So this choice letter C here, this is equal to what we have since this is 80 times 1 plus 0.06 to the third, or writing it most simply, this is 80 times 1.06 raised to the third power. So choice letter C is the correct answer here.